So, good morning, everybody. Let's start with our lecture today. Today we talk about transfer functions, poles, zeros, step responses, and simple feedback loops. This starts going into the logistics business using math. Okay, so we have some notation. That we need to refer to when we have a system. We talk about R of t, like the reference function or input. It could be some demand, some changes in the inventory. We have I of t, which is the output function that we measure. We have v of t, which is the variable. Or controlled output. Something we do in the system. D of t, we are going to call disturbance. Things happening to the system. And u of t, we already know, is the step function. Okay. So as we will very soon see, this goes straight into the logistics world, because logistics is all about controlling an output based on a variable input. And for this we use the concept of transfer function. Okay, this is an important concept. Before I explain what a transfer function is, a little note, okay? The meaning of 2 divided by 3 is equals 0.6. This is a super simple fraction, but it contains the concept of transfer function. This 2 divided by 3 means how many times two is contained in 3. Okay, you see that? So 2 is 0.6 times 3. Okay, and this is the concept of a transfer function. So let's call it TF. A transfer function in the complex domain is a ratio. G of S is a ratio between the output and the input. Okay, so it means how many times the output is contained in the input. In other words, given a change in the input, for instance in the demand, how does the output change? Okay, if you have let's say a warehouse, okay, that is getting a change in the demand, is getting an input function and is delivering some materials, how many times the input is contained in the output. How does the system react to changes? Okay. Let's create here a first order model. Okay. Imagine we have a system that, let's say, I'm going to paint here a little factory. Okay, just we have here some function r of t, some maybe input in the demand, and then we have an output, how the factory behaves. Okay, and we are going to say our factory behaves in a first order manner. Oh no, I forgot to say that this is only true for 0 initial conditions. Okay, this is important for math, but this is the usual case in the engineering system. So we have r of s, we have y of s, and we know that our model is first order, so we are going to describe it like this. Tau, time constant, first derivative of the output plus the function output equals some constant k, and then the system there. Okay, so we want to know what is the transfer function here. Yeah, for initial conditions 0. Okay, so we apply the Laplace transform as we know, and this becomes tau s I of s plus I of s equals k r of s. Okay, and then we factor I of s. This yields that our transfer function y of s divided by r of s equals k divided by 1 plus tau s. All right, so this is our world, and this is a useful result because we're going to use this to solve following problem. Now imagine our input function r of t equals the step function. Okay, so equals 1 for t bigger than 0 and 0 for t smaller equals 0. In other words, we are inputting to our factory a step demand change, let's say. Okay, if this is time, this is r of t. Okay, we are inputting a certain step function. because our function is multiplied by k, we can say this is k times r of t. Okay, so we are inputting this into the factory, and what we want to know is what is the output behavior. Okay, we want to know what is the output behavior. Okay, so because g of s, let's solve this, is y of s divided by r of s equals k 1 plus tau s. We can say that I of s equals r of s times k divided by 1 plus tau s, because the Laplace transform of r of s is of the step function is 1 divided by s. We have that it becomes true. Okay, this is the Laplace of step function. Well, we can rewrite this I of s equals k divided by tau times 1 divided by s times 1 divided by s plus 1 divided by tau. Okay, I've just taken tau out of the system so that we can apply the transfer function, the Laplace function, easier later on. So this we can transform into a divided by s plus b divided by s plus 1 divided by tau. Okay, and so if we do this, we can say that k divided by tau equals a multiplied by s plus 1 divided by tau plus b times s. Okay, so if s becomes 0, then k divided by tau equals a times 1 divided by tau, so a equals k. If s equals minus 1 divided by tau, then k divided by tau equals minus b divided by tau. So b equals minus k. So as a result, we have that I of s equals k multiplying 1 divided by s minus 1 divided by s plus 1 divided by tau. If we do the inverse Laplace transform, I of t equals k multiplying 1 minus e minus t divided by tau. Okay, and this is the output of our first order system. If we paint it here, for t equals 0, this becomes 0. So let's do it in a different color. Becomes 0 for t equals 0, and for t equal infinite it becomes k. Okay, so and tau is going to be the please switch off your microphones. If you don't have questions, switch off your microphones, please. Okay, so this is our first important result. Do you have any questions on the way I solved this? So we called k the static gain, and we called tau the time constant, how fast the system reacts. Okay. So, a general transfer function has the form g of s equals n of s divided by d of s. And n and d are the polynomials, okay? Numerator and denominator. So the zeros are the roots of the numerator. So n of s equals 0. The poles are the roots of the denominator. D of s equals 0. And the order of a system is the degree of the denominator. Okay. This is just some definitions. And now I'm going to give you a stability rule for linear systems. Cool. So if all poles all satisfy that the real part of the pole is smaller than 0, then the linear system is stable. If one pole has real part of the system of the pole bigger than 0, then the system is unstable. Okay. So poles determine the natural dynamics, and whenever you describe or design a logistic system, you need to take care of the poles and the zeros, okay? Because this is going to determine its behavior. And zeros shapes how the input enters the output. This is important because students often remember poles but forget the zeros, okay? And this is you cannot allow this to happen. Okay, so now let's analyze a second order transfer function. We have analyzed a first order transfer function. Let's analyze the second order transfer function, and this will give us more insights. So imagine we have a system, second order. How did I call it? Second order model. And a step response to it. Okay, so now imagine we have a system that it's not first order but is second order, so it gets again a an input. I'm gonna put it in the time domain first. It's more intuitive. It gets an output, and the input out and the output is second order. So or the system behaves in a second order manner, better said, which would be something like the second derivative of t plus 2 times omega sub n xi first derivative of t plus omega, and the function equals omega square okay. So this is the usual form that these functions get in engineering. And this is going to yield a transfer function g of s I of s divided by r of s equal, if you do the Laplace transform, and so of omega square divided by s square plus 2 times xi omega sub n s plus omega sub n square. Okay, as we have seen in previous lectures, the damping classification appears. If C is bigger than 1, it's overdamped. If C is 1, is critically damped. If 0 smaller than C smaller than 1, this is underdamped. And if C is 0, this is undamped. So how does it work and how do we solve it? If we have a, again, step function, input, okay, let me put again same here. So here we have k times r of t. This is t. Okay, and this would be k if the system behaves in this second order manner. How is the behavior of the output? Okay, so let's do it. We have that I of s equals r of s times w sub n square divided by s square plus 2 times xi w sub n s plus w sub n square. This equals k divided by s times w sub n square divided by s square plus 2 times xi w sub n s plus w sub n square. Okay. So this is the way we would now do the calculations. Let's take the w sub n in an example to do the calculations faster. Let's take w sub n equal 2 and 2 times xi w sub n also 2. So meaning that he would be 1 divided by 2. So we have this, our, I mean, sometimes it's easy. I could do it with parameters, but sometimes it's easier to do it with numbers. So w sub n squared will be 4 divided by s squared plus 2 times s plus 4. Okay. So this would mean if we want to separate this s squared plus 2s plus 4 equals 0, the poles of that is minus 2 plus minus 4 minus 16 divided by 2. this becomes minus 1 plus minus j root square of 3. Okay. So if we input that up there, we got 4 times k times 1 divided by s times s minus 1 plus j root square of 3 times 1 divided by s minus 1 minus j root square of 3. Okay. And we perform again with our separation so that we can apply the Laplace transform easily. Okay. So as a result, we have that for k equals a times s minus 1 plus j square root of 3 times s minus 1 minus square root of 3 plus b times s minus 1 minus j square root of 3 plus c times s minus 1 plus j square root of 3. Okay. If s equals 0, then we have that for k equals a times one minus j square root of 3 times 1 plus j square root of 3, and this becomes a times 1 square plus square root of 3 square equals a times 4. So a becomes k. Okay. If s becomes minus 1 minus j square root of 3, then we have that for k equals c times s plus 1 plus j square root of 3 wait, let me put it here. This is s, and then times s minus 1 plus j square root of 3. So this yields c times 1 plus j square root of 3 times 2 Okay, so we can say that C equals 2 times k divided by 1 plus j square root of 3. If we multiply by the complex conjugate, this equals k divided by 2k divided by 4, so k divided by 2, 1 minus j square root of 3. And this is C. Okay. If we say that S equals wait. No, sorry, this needs to be plus. This is wrong. This is a plus there. So let me correct this. This is not correct. This is not correct. Otherwise, it's not 0. So let's do it again. Sorry for the mistake. So we want this to be 0, and we want this to be 0, so that's why. So this needs to be a plus. So 4k equals c times minus 1 minus j square root of 3 times minus 1 minus j square root of 3 minus 1 plus j square root of 3. This yields c times minus 1 minus j square root of 3 times minus 1 goes with plus 1 minus j square is plus 1, so this is 3. As a result, c equals 4 divided by 3 k times 1 divided by minus 1 minus j square root of 3. We multiply by the complex conjugate. This equals then 4 divided by 3 times k times minus 1 plus j square root of 3 divided by 4. So c is going to be k divided by 3 minus 1 plus j square root of 3. Okay, so this is correct. So, and for the other value, we want the c to be 0, so we want it to be minus 1 plus j square root of 3. So 4k equals b times minus 1 plus j square root of 3 times minus 1 plus j square root of 3 minus minus 1 minus j square root of 3. So again, this becomes minus 1 goes with plus 1, This becomes b times minus 1 plus j square root of 3 times plus j minus j square is plus 1, 3. So b becomes 4k divided by 3 times 1 divided by minus 1 plus j square root of 3 times the complex conjugate. And as a result, we get we get 4k divided by 3 times minus 1 minus j square root of 3 divided by 4. So b is going to be k divided by 3 times minus 1 minus j square root of 3. Okay. So finally we have our solution. A divided by s A was k, so plus b k divided by 3 minus 1 minus j square root of 3 times s minus and then z is k divided by 3 times minus 1 plus square root of 3 and then the root there s minus 1 minus square root of 3. Okay, so we do the inverse Laplace transform on this and we get that I of t equals k plus k divided by 3 minus 1 minus j e minus minus 1 plus j square root of 3t plus k divided by 3 minus 1 plus j square root of 3 e minus 1 minus j square root of 3. Okay. So the behavior, if we do t0 for e equals 0 is k plus k divided by 3 minus 1 minus j, the thing is 0, and then plus k divided by 3 minus 1 plus j. Okay, so k plus minus k divided by 3 minus k divided by 3, so we get k divided by 3. So in I equals 0, the system is going to So, bitte eure Mikrofone stumm machen. Dankeschön. The system reacts with k divided by 3 for t equals 0. And when t equals infinite, the system is going to be giving the value of k, okay, because these things are going to cancel. So we know that this oscillates, and as a result we can say this behaves like qualitatively like this, okay. So it's an oscillation that is going to end up in the value k. This is how the second level system works. Okay. Good. Any questions? Okay, so now we go to the simple feedback loop. And you will see, maybe you've heard of some concepts like Kanban in logistics. You will see that many logistics systems are just feedback loops. We're going to learn how to treat them mathematically. Okay. So imagine we have a following system, not just a straight line, okay, but a system in which we put some input there, some demand or some inventory regulation, okay. Then, so, ich möchte euch bitten, eure Mikrofone auszuschalten. We have a control system there in place. Okay. Then we have a system itself that yields an output. But we take this output and we insert it here back with a minus to control our system. Okay, this is the very basic foundation of what we call Kanban in logistics. So as a result, we're going to get an output here called ES. Okay. Oh no, and I installed also here some intelligence into the feedback loop. Okay. So what we call the error here is going to be the input minus So the input goes with a plus, minus I times H. Okay. Error is E of S. The output of the controller we are going to call V of S. So V of S equals the error times C and the output of the plant is going to be Y of S is going to be our system definition, our transfer function, as we saw before, times V of S. So V of S multiplied by G of S. If we substitute, we get that I of S equals G of S multiplying E of S times C of S. I've just substituted V here, okay? But now I can also substitute E of S. So this is G of S times C of S times the error, but the error is R of S minus Y of S times HS. Okay. So this is again G of S times C of S times R of S minus G of S times C of S times H of S times Y of S. Now I take Y out. So I of S multiplies 1 plus G of S, C of S, H of S equals G of S times C of S times R of S. And so the transfer function I of S divided by R of S equals G of S times C of S 1 plus G of S times C of S. Times H of S. But usually the H of S is transformed as 1 because of clarity reasons. So the general function becomes G of S times C of S divided 1 plus G of S C of S. Okay, and this is the feedback loop. This is the transfer function governing almost all feedback loops. We have a controller, we have a system, we have an output, and we have a feedback loop. And this, my friends, is the very basics of logistics. Okay. This improves tracking, reduces sensibility to disturbances, speed up response. The downside of it is that if it's too aggressive, it can create oscillations. Maybe you've heard of bullwhip effect. Yeah, but that's downside we are ready to take. Okay, so we need just to calibrate it. Any questions? Okay, so now let's interpret this whole thing in terms of logistics. Closed loop example. Inventory or throughput regulation. Okay. So R of t. Now I'm going to use we're going to use the language of logistics. Okay. So R of t is the desired throughput. And Y of t is the actual throughput. You can think of the desired throughput as the demand, okay? Something that a customer wants. I am in the factory. I get some demand in, and I want to regulate my throughput. And I am going to do it by installing a feedback loop. So the plant is first order. So G of S is K divided by tau S plus 1. Or K sub P. The controller is proportional. So C of S is K sub C. And we assume unity feedback. So the transfer function T of S equaling Y of S divided by R of S is going to turn K sub C times K sub P divided by tau S plus 1 plus K sub C, K sub P. Why is this? Let's do it more slowly. So we have R of S. We have here our controller, which is in reality a constant. We have our transfer function k sub p tau s plus 1. We have our output. Okay, and we have said that the transfer function is the multiplication k sub c times k sub p divided by tau s plus 1 divided by 1 plus the same k sub c k sub p tau s plus 1. So if we refine this a little bit, we get k sub c k sub p divided by k sub c k sub p plus 1 plus tau s. Okay. Good. If we repaint this a little bit, we can say this is k sub c, k sub p divided by, put it a little bit better, k sub c, k sub p divided by tau times 1 divided by s plus 1 plus k sub c, k sub p divided by tau. Okay. If we say we have a step input, same question as before. If we have a step input r of t, and then create, let's say, a step input k, the question that arises is how this closed feedback loop is going to change the response as compared with the above, with the open loop. Okay, so if we have the I of s equals r of s times the transfer function, we have here k divided by s, just as above, and then we have all our transfer function here. We know that the solution of this is of the form k times k sub c, k sub p divided by tau times 1 divided by s times 1 divided by s plus 1 plus k sub c, k sub p divided by tau. This equals a divided by s plus b divided by s plus 1 plus k sub c, k sub p divided by tau. Okay, so k times k sub c times k sub p divided by tau equals a times s plus 1 plus k sub c k sub p divided by tau plus b times s. So if s equals 0, then k times k sub c k sub p divided by tau equals a times 1 plus k sub c k sub p divided by tau. So a becomes k sub c k sub p divided by 1 plus k sub c k sub p. If s equals minus 1 plus k sub c k sub p divided by tau, then k sub c k sub p divided by tau equals minus b times 1 plus k sub c k sub p divided by tau. So b equals minus k sub c k sub p divided by 1 plus k sub c k sub p. So as a result, our function becomes k sub c k sub p divided by 1 plus k sub c k sub p multiplies 1 minus 1 divided by s plus 1 plus k sub c k sub p divided by tau. So, and in implementing the inverse Laplace transform, we have that I of t is 1 divided by s. We're still in the s domain. K sub c k sub p 1 plus k sub c k sub p, and here is 1 minus exponential of minus t times 1 plus k sub c k sub p divided by tau. Okay, this is the general form of the first order control loop. If we look above in our notes, the solution we got was k times 1 minus k times 1 minus a minus t divided by tau. Okay, this is the open loop, first order open loop. Okay, so this is above. You see the effect taken by these constants. Okay, if we say k sub c or k sub p are very small, or k sub c divided by k sub p is equals 1, then this turns into 1. Well, it depends on the constants, I guess. It has a a different behavior depending on the constant. Qualitatively, it just turns out that when t equals 0, this becomes 0. Okay, so the qualitatively behavior is again 0, it's first order. And then when t is infinite, it's going to turn out to be k times k. It's not going to end up in k again. This value is going to be k times kc, kp divided by 1 plus kc, kp, which is this constant here. Depending on the values of kc or kp, you will get higher than k or lower than k. Okay? So this is the first order response of our system. Why logistic engineers care? Okay. This is useful for inventory regulation. This is useful for release rate regulation. This is useful for backlog reduction. This is useful for conveyor control. This is useful for warehouse climate control. This is useful for understanding oscillations in supply chains. Something called bullwhip effect. Maybe you've heard of it. We will look at that later on. Okay. This is useful for a fuckload of things. So make sure you internalize these concepts because they are essential for your future. Good. Any questions? No. Good. Tomorrow we will look at several logistics replenishment dynamics using this. So I mean, I think now it gets interesting for you. Until now it was a little bit abstract or just math, but now it starts getting interesting. Make sure you internalize the concepts before, okay? Well, I stop here and I will upload the information in a couple minutes. Thank you. Please be on time tomorrow, okay? On time means 2 minutes before the lecture, you're all online. Thank you. Bye-bye.